In this video, we will use both Excel and Minitab to perform a one-proportion binomial test to test whether the observation of 37 female frogs out of a total of 50 frogs is more than would be expected by chance if the individual probability that each frog was female was 0.6. We start in Excel by calculating the probability of observing specific numbers of female frogs using the null hypothesis of a probability of 0.6. So we enter the total number of frogs, 50, in D2, the probability that each one is female, 0.6 in D3, and we will use the binomial probability distribution, which is given by Binomial Dist in Excel. So to start in C6, we will calculate the probability of observing exactly 15 females. And to do this, we will enter the binomial distribution function, which requires the number of observed, which is 15 in B6, the number of trials, which is the total number of frogs, 50, the individual probability, which is in D3. We do not want the cumulative probability, so we enter false, giving an individual probability of observing 15 female frogs as 1.249 times 10 to the minus 5. Now we're going to copy this calculation to all the other rows, but we need to lock the row reference to both the total number of frogs and the probabilities in D2 and D3 by using the dollar sign, and then we can copy this to all these other possible numbers of female frogs, and the chart now plots these probabilities for each of the specific numbers of possible observations of female frogs, showing, as we would expect, that if the probability of a female frog is 0.6 out of 50, the most likely number observed will be 30. For this particular test, we want to calculate the cumulative probability of observing either 37 female frogs or more. So we need to add up all of these probabilities from 37 onwards, and to do that we'll just copy these values into an adjacent column. So we need to add up the total area under this upper tail from 37 onwards. We can do that just by adding up the values that we've calculated so far, giving a total probability of 0.0280. However, this is not absolutely accurate because it doesn't take into account the very low probabilities of observing 46 or more frogs. Just for completeness, we can calculate this total area of the tail more exactly by starting with a total area of 1 and then taking away the cumulative area up to 36 female frogs. And for this cumulative area, we will again use the binomial distribution up to 36 frogs, again with 50 trials, with a probability of 0.6, only this time we will select the true option. So we are taking away the cumulative area up to 36 from 1, which will give us the tail area from 37 onwards. This gives us, to 4 significant figures, the same value that we have already calculated. This then is the probability that we could observe 37 or more female frogs by random chance. This value of 0.0280 is then the p-value for this one proportion test. To calculate the two-tailed value, we will have to add up the probabilities of observing 22 or less female frogs, so we can perform a similar calculation at the lower tail, this time going up to 22, and just taking the simple sum again, this gives us a lower tail area of 0.0160. These values are not the same in this case because this is not a symmetrical distribution. But then the total area of 0.0160 plus 0.0280 giving a p-value of 0.044. We will now see the same results obtained using the Minitab analysis. We can use Minitab to perform the one proportion test by going to Stat, Basic Statistics, one proportion, and we assume that we have summarized data and that we have observed 37 events out of a total of 50. That is, 37 frogs out of a population of 50 were female, and we wish to perform a hypothesis test to compare the observed proportion with an expected proportion of 0.6. We can go to Options, and we can either make this a two-tailed test, where the alternative is that it is not equal, or a one-tailed test greater than or less than. And in fact, we're looking to test whether our observed proportion is greater than the expected value of 0.6. We can also choose to make the test based on the normal distribution. So we could click here for the normal distribution test. We click OK, and then we run the analysis. The result appears in the session window, where it is a one-tailed test of the proportion being equal to 0.6 or greater than 0.6. The results given show that our sample proportion was 0.74, and it calculated the Z value of 2.02. It also calculates the p-value for this test of 0.022, which for this particular analysis, which suggests that we should reject the null hypothesis that the true proportion was 0.6 and accept that our experimental proportion is significantly greater than 0.6. We can repeat the test to use the alternative method, and so we unclick the request to use the normal distribution, OK, and run the analysis again. This time it uses the binomial test to calculate the p-value and obtains a p-value of 0.028, which again is a significant result, saying that we should reject the null hypothesis.